Hello everyone. It's my pleasure to be here and present our work, confidence-rich localization and mapping based on particle filter for robotic exploration. Robot exploration plays a unique and important role in deep-sea or planetary exploration, field rescue, and other tasks. In these environments, we often do not have enough prior map information, so we often encounter the problem of a robot deciding where to go next. As a simplification, first, we consider a robot exploration problem in a two-dimensional environment, as shown in the bottom figure. At this time, the robot is at a fork in its road. Where should it go? North or east? How to make a decision? Now we consider this problem from the perspective of information theory, that is, we choose the travel action that can maximize the information gain under practical constraints such as energy consumption, localization uncertainty, and traversability. This has also led to a new problem: how to define the information more precisely and efficiently. In the previous literature, people used Shannon entropy mostly. Recent studies mainly involve OGMI, CSQMI, GPMI, FSMI, CRMI, etc. But they all assume the robot's poses are known via an independent localization method. However, this assumption is difficult to realize in several severe environments. For example, unstructured scenes lack easily extractable features, such as planetary surface, unstructured seabed, and featureless caves. In fact, pose uncertainty is quite important in exploration, as in the figures below. A robot who can be aware of its pose uncertainty will prevent itself explore unknown areas greedily and aggressively for safe, such as Action 1. It also will leave the already explored place such as Action 2. So how to consider the pose uncertainty explicitly? There are many related works. Borgalt first calculated the pose uncertainty in an EKF-SLAM framework, and Stackness proposed a classical method to approximate the trajectory entropy via a motion model. Recent works are mainly based on this method, such as Valencia and Popovich. But these pose propagation methods always overestimate the pose uncertainty by the manually set covariance. This motivates us to propose a more accurate method to approximate the pose uncertainty and ensure efficiency. The main contributions of this work are threefold. We propose an RBPF-CLAM method for localization in confidence-rich maps, CRMs, which is suitable for unstructured or featureless scenes. We also present a closed-form importance weighting approach for particles based on continuous distribution over occupancy. Finally, we use weighted particles approximation to incorporate pose uncertainty with CRMI. Now we move to the methods. This slide presents the basis of CRMs. In a CRM, each grid cell owns a continuous occupancy M and a belief distribution B M over the occupancy. CRM considers the dependencies between the measured grid cells and provides more occupancy information. Here is a simple example to show the evolution of a free cell after it gets observed from 0 to many times. The peak of its occupancy distribution is constantly shifted to the left, that is, the low occupancy value direction. The update equation works recursively and M hat is the mean occupancy value. We first introduced the basic particle filter-based localization of CRMs. For an RBPF method, the pose and map posterior updates are factorized independently. So, the key point is to estimate the pose. This is the basic procedure of an RBPF. We set the particle set containing NP particles. Each particle contains the robot pose X and its weight omega. We first sample the candidate pose for particles using the odometry model, then update the weights using the classical scan matching method and a measurement likelihood as a backup if scan matching failed. Then we resample the most effective particles and update the confidence-rich map using the estimated pose. In the importance weights update procedure, the proposal distribution in the scan matching process is suboptimal, especially when the onboard sensor measurements are more accurate than the odometry estimates. Instead, we can take the advantage of the continuous map belief in CRM to improve the weight computation and the localization accuracy. According to the sufficient statistic property of map belief BM, we can substitute this term by a simpler one, so we can get the new closed-form way to update the weights for beam-based sensors, wherein Z is the number of the beams in one scan. Next, we can use the particles to do more things, such as to approximate the pose uncertainty. Traditional methods for calculating the pose uncertainty mainly only use weights and ignore the pose info, which is quite coarse. Instead, we do this in a more accurate Bayesian way. The information gain over path can be factorized into two terms. The left term can be approximated by the weighted particles like this, and the right term can be approximated like this. Then we get the trajectory information gained by the difference between two consecutive path entropies. The new information function UCRMI can be constructed by a linear combination of trajectory info gain and CRMI, where alpha is the constant for balancing mapping and localization and it depends on a certain task. Now we present some simulation results. In the first simulation, we compare the localization performance of RBPF CLAM and RBPF OGM in the museum dataset. We use low sensor configuration to simulate a poor sensor. The results show our RBPF CLAM performs better than RBPF OGM, especially around corners and cluttered rooms. The main reason lies in the scan matching failure in traditional RBPF OGM at these places, and our closed-form weighting method still works at this case. In the second simulation, we compare our UCRMI with four other important information functions, such as OGMI, CRMI, GPMI, UGPVR. We use a robot equipped with a poor sensor to plan a most informative path in the cave map under the limited travel budget. Monte Carlo simulations show that RBPF CLAM works well for the reduction of pose uncertainty in exploration. UCRMI has similar trends to CRMI, and plans the longest informative path and owns most nodes or samples than others, which means UCRMI can conduct more prudent and fine exploration. The results also show UCRMI gains computational cost than CRMI, but is much smaller than UGPVR, which is also acceptable. Our future work mainly involves studying the value of alpha, planning online in unknown environments, and speed up the computation of UCRMI. Thanks for your time and welcome the questions.